Welcome my dear students. Today we will be discussing on a new module which is dynamics of electric drive. So what is dynamics of a motor load combination? So when an electric motor rotates, it usually is connected to the load which has a rotational or translational motion. So rotational motion is obvious for any type of rotating machines, but we also saw that translational motion is also possible in case of electric machines. That means if by some sort of a gear arrangement we can design one load which can travel or which can move linearly, then it is a translational motion. Also, there is a special type of induction motor which is known as LIM or linear induction motor. It also exhibits translational motion. So, the speed of the motor may be different from that of the load. To analyze the relation among the drives and loads, the concept of dynamics of electric drives is introduced. So, to analyze the relation between the drives and the loads, so actually, what is a load? The load is actually the requirement of a machinery industry. Actually, for any type of industry, be it a paper mill, be it a cement mill, be it any type of mills, so the load requirement is different. So let us let me cite with an example. Suppose for one industry, suppose the load torque is represented like this. So the maximum is say 15 Newton meter and the minimum here is 10 Newton meter. So let us say for 5 seconds it is 15 Newton meter, for the next second it is, or the next 5 seconds it is 15 Newton meter, or vice versa. For the first 5 seconds it is 15 Newton meter, for the next 5 seconds it is 10 Newton meter. So this is called the load torque profile or the load profile. So it is very much industry specific. Suppose for another type of industry, it is like this. So this is 10, this is say 15, and this is 5. So for the first 2 seconds, let us say it is 10 Newton meter. For the next 2 seconds it is 5 Newton meter. For the next 2 seconds it is say 15 Newton meter. So this is the requirement of another industry. So the speed of motor may be different from that of the load. So the speed of the motor may be different. It is not necessary the speed of the motor and the speed of the load is same. So let us see with the help of an example. Suppose you are having a motor, say like this. It is connected to some converter C, but the supply of the converter is say V. So you are getting some voltage Vs to the motor, and the motor is moving say at a speed of 100 rpm. Now suppose there is a gear like arrangement. So let us say that the radius of the first gear, which is directly coupled with the motor shaft, is R1, and the radius of the second gear, it is say R2. So now the load is connected which is tau L. It is connected to R2. So the teeth is different. It is not necessarily that the load is directly coupled to the shaft, but it is indirectly coupled to the shaft by means of a gear. So let us say it is 100 rpm, and so if it is 100 rpm, so the teeth ratio with respect to 100 rpm, it should be, suppose it is R1, it is R2, so the number of teeth here is N1, this is N2, so the teeth ratio A, it is equal to N1 by N2. So the speed of the load, that is omega L, is equal to function of teeth ratio and the rotor speed omega R. So it depends on the teeth ratio. So the load speed is not equal to that of the rotor speed. And when you are analyzing such type of motion, it is known as dynamics of electric drives. So the motor load is different for different types of loads, and the concept needs to be analyzed, it needs to be visualized very well in order to comprehend the operation of the electric drives, because it is all about motion dynamics. So now this is an example of a motor load system. So let me elaborate this diagram. So there is a motor, and this motor is connected to a supply Vs, and when it is connected to a supply, it may be a DC motor, it may be an AC motor. As it is connected to the supply, so what is happening, it is producing a motor torque which is given by tau, and it produces a motion which is given by this direction whose speed is omega m, and the load is directly coupled to the motor shaft. So now the torque and the load torque, they will be opposing one another, they will act in opposite direction. If the load torque acts clockwise, the motor torque will act anti-clockwise, and vice versa. So this is the dynamics. So the load will always oppose the motor rotor. So let us say these are the symbolic notations which is used. So J over here is the polar moment of inertia of the motor load. Omega m is the instantaneous angular velocity. Tau is the instantaneous value of the developed motor torque. Tau L is the instantaneous value of load torque referred to the motor shaft. So these are the notation that is used while deriving the equation. So now if the motor torque is tau, so as per dynamics, the net torque is tau minus tau L, and that is equal to ddt of j omega m. So if you make a derivative of this particular j omega m, it will be j dot omega m plus j omega m dot. But you see the constituency of the rotor does not change, and the rotor is fixed. So obviously, as the rotor is fixed, the moment of inertia of the rotor, it is also fixed. So I can say that the derivative, that is j dot, that is dj dt, that will be 0. So what we are left, that is equal to j omega m dot. So this is equal to j d omega m dt. So this is the first order ODE. Now if I try to represent it like this, it will be tau minus tau L, that is equal to J d2 theta dt2. So theta is the angular displacement. Am I clear? It is the angular displacement. So what is this? This is a second order ODE. So now what is the implication? The above equation states that the motor torque is balanced by the load torque, which is tau L, and a dynamic torque. It is J d omega m dt. This is the dynamic torque. So this torque component is termed as the dynamic torque as it is present only during the transient operations. So from this equation we can determine whether the device is whether the drive is accelerating or decelerating. So obviously, so if omega m dot, if it is greater than 0, it is accelerating. So if omega m dot, if it is less than 0, it is decelerating, and if omega m dot equal to 0, then from here we can derive that omega m is equal to constant. That means in that case tau is exactly equal to tau L. That means the rotor is moving with constant speed. Only then it is possible. So any unbalance of tau and tau L, it will be reflected in the dynamic torque, which is this one. Either it will be positive or it will be negative. If it is positive, then it is accelerating. If it is negative, it is retarding. So this is the dynamics of the electric drive. Such as during the accelerating motor supplies the load torque and additional torque component essentially. So you see what is the requirement. So the motor torque tau, that has to be equal to the load torque plus this J d omega m dt. So that means the torque that has to be generated by the motor during the motoring operation has to satisfy this load torque and this transient torque. Now this is for the acceleration. So what will happen if it is minus? That means it is retarding. So you see that the torque requirement of the motor is greater during acceleration, and the torque required by the motor during retardation, it is lesser, as this value is decreasing because a minus sign is there. So that means during acceleration, the power that is drawn from the supply, that is greater, whereas the power that is drawn from the supply during the retardation, it is lesser. So that means deceleration means negative acceleration, and it is also called electrical braking. It is also called electrical braking. Now if we see the load torque equation, or the fundamental torque equation, so the drive is said to be in equilibrium, or your electric drive is said to be in equilibrium when tau is exactly equal to tau L. So this is the equilibrium condition. So this is known as the equilibrium condition. So the drive is said to be in equilibrium if the torque developed by the motor is exactly equal to the load torque. If the drive comes out of the state of equilibrium due to some disturbance, it comes back to steady state for stable equilibrium, but for unstable equilibrium the speed of the drive increases uncontrollably or it decreases to 0. So that means an important thing is the disturbance in the system. So it comes back to steady state for stable equilibrium. The system will be stable, but it will be unstable if the speed decreases or increases rather uncontrollability, or it decreases to 0. This is known as unstable equilibrium. So stability analysis during any disturbance, it is very important from the fundamental load torque equation, and graphically we have to analyze the stability of the system. That means the motor load system. The stability analysis has to be performed. So you see, when the drive is coming out of the state of equilibrium, it preserves its steady state at different speed lying in small range. It is said to be in neutral range. The stability of the motor load combination is defined as the capacity of the system which enables it to develop forces of such a nature to restore equilibrium at a very small departure. That means, suppose the motor torque is tau and the load torque is tau L. Now there is an incremental disturbance in the motor so that the torque increases to this proportion. So the change in the load torque will be such that the equilibrium is restored after a very small incremental departure. Only then it is said to be in stable equilibrium, otherwise not. Now the changes from the state of equilibrium, when it takes place very slowly and the effect of either the inertia or the inductance is insignificant, it is called steady state stability. That means when there is a state of equilibrium, that change takes place very slowly and the effect of either the inertia or the inductance is insignificant, it is known as steady state stability. But when there is a sudden or fast change from the equilibrium state so that both the inertia and inductance cannot be neglected, it is known as dynamic or transient stability. So this is slow, this is sudden. So I think we should stop now for today. So see you in the next lecture. Thank you.